Hi, thank you for joining us for today's virtual workshop. My name is Nam, and I'm the Partner Development Manager at Vorum. I have the pleasure of working with new customers, introducing them to our digital technology, and exploring the various ways our powerful solution can address their specific needs. Vorum is the leading provider of a quality turnkey digital solution for orthotics and prosthetics. And today, we are presenting The Future is Additive, adopting 3D printing technologies for your O&P practice. Just a little housekeeping before we get started. If you have any questions or thoughts during the presentation, please type them into the chat box. Once we see any questions show up, our team will do our best to answer your inquiries in real time. Now, without further ado, let's get started. The disruptive world of additive manufacturing is one that many consumers have had their eyes on these days. When it comes to technological innovation, design freedom, and hardware accessibility, 3D printing can empower manufacturing industries with the tools to take their production to the next level. It's no surprise that the field of orthotics and prosthetics can also benefit in the same manner. In fact, because the entry to 3D printing is fairly low for the average consumer, more and more O&P professionals these days are trying out the unique technology for their own practice. Our dedicated team has also been working hard to evaluate the potential benefits and drawbacks of additive manufacturing technology. This workshop today will highlight some of those developments we've made on the 3D printing side of things, as well as some of the findings we've discovered through our R&D initiatives. For some of you who aren't familiar with our company, I'll be going over who we are and what Vorum has done to support orthotics and prosthetics over the years. After that, I'll be handing the presentation over to Chris Sokoloff. He's one of our experienced implementation specialists who will be discussing some of the different types of 3D printing methods and the applications associated with each procedure. Following him will be Taryn McCready, another one of our hardworking implementation specialists who will discuss some of the valuable information regarding how to properly implement CAD/CAM and/or 3D printing technology into your practice. Next, we'll highlight some of the new 3D printing tools available in the latest version of our CanFit design software. And there would be no one better to do this than one of our own diligent software developers, Paul Lorre. Finally, the presentation will conclude with us elaborating on some of the experiences we've had with additive manufacturing technology and discuss some of the biggest learnings we've made to date. Chris Hanford, Vorum's product manager, and Jeffrey Chang, our senior R&D engineer, will take on these topics respectively. Let's begin with a question. Who is Vorum and what do we do? Vorum was the first company to introduce CAD/CAM technology into orthotics and prosthetics. For years, the company pioneered and drove new digital outlooks for the industry. Being the first to market with 3D scanning, CAD software, and carvers, Vorum's technology revolutionized the way these clinical devices would be fabricated by giving O&P professionals a novel set of powerful tools to work with. People who took the initiative to implement a Vorum solution reaped the benefits of achieving amazing improvements in workflow efficiency and better clinical outcomes. With over 30 years of exclusive commitment to the field, Vorum continues to be the solution provider that people acknowledge and appreciate when it comes to quality. It goes without saying that Vorum offers the most trusted, turnkey digital O&P solution in the world. Despite its introduction over the past few decades, CAD/CAM technology is still not widely understood in orthotics and prosthetics. In fact, about 96% of O&P professionals believe that people in the field have either a vague understanding or a general understanding of how CAD/CAM is used in the industry. Only a minute percentage actually believe people have a full comprehension of its usage. Personally, I think this is one of the biggest reasons why digital technology is still not widely used in the industry. So let's change that. The word CAD/CAM can be broken down into two parts. CAD stands for computer-aided design. It is a process of creating and designing a product or prototype within a virtual environment. CAD is normally operated through software that allows the user to make intricate modifications and improvements to the quality of a design. The design itself can be two-dimensional drawings or three-dimensional shapes. Lots of different professions use CAD. An example could be an engineer using CAD to model all sorts of things, such as a fluid flowing through a valve. Another example are architects who can use CAD to digitally draw and modify designs instead of drawing things by hand. CAM, on the other hand, stands for computer-aided manufacturing. Similar to CAD, this process involves the utilization of computer software to control machine tools to automate manufacturing processes. These software applications basically create detailed instructions for machines to follow and operate. Because both CAD and CAM require computer-based systems to work, the designing and manufacturing processes can easily integrate with each other. Since different machines also have different numbers of axes with different dimensions and orientation, a given CAM program has to be calibrated with the specific machine it's talking to. In 3D printing, CAM software is often referred to as slicer software. Together, these form the foundation for a new workflow or even business model. More importantly, in our field, where detailed clinical modifications, customized patient devices, and intricate fabrication processes are required, orthotics and prosthetics can also make great use of CAD/CAM's capabilities. This leads us to our next question. Just how is the technology used in orthotics and prosthetics? The CAD/CAM process is fairly straightforward and is composed of 3 key steps. It begins with the utilization of a 3D scanner to capture the shape of the patient's body that requires clinical attention. In some occasions, a clinician may consider scanning a cast instead if the patient cannot assume certain positions for correction. Scanning is also usually pretty fast and doesn't require much involvement from the patient, though it is important to ensure that the patient is comfortable and fairly still during the scanning step. Large movements or changes of the shape or position of the limb during the scan may result in the need to redo the scan. The next step is designing the O&P device on CAD software. This part is essentially the digital version of the traditional plaster room. Scan files are opened in these CAD programs to allow O&P professionals to modify the shape according to the patient's clinical needs. As mentioned previously, CAD/CAM is widely used in numerous industries, so there's many options available. Unfortunately, however, most generic programs are extremely technical and often have tools irrelevant for O&P work. That's why companies like Forum exist, to provide a simplified and applicable digital solution for orthotists and prosthetists like you, so they don't have to waste time evaluating what systems would work best for your needs. The final step requires the modified shape file to be sent to a CAM software, which will create a toolpath for a machine such as a carver to operate accordingly. The file allows the carver to mill out the exact shape of the device designed on the CAD program using materials such as dense polyurethane foam. Once the mold is carved out, there may be some finishing touches required to get the mold prepped before traditional O&P fabrication. Looking at it once again, the CAD/CAM process consists of 3D scanning patients or casts, digital rectification, and mold carving. An O&P facility that wants complete control over the end-to-end process would consider owning each of these steps in-house. Having an in-house digital solution allows you to better streamline and optimize your workflow. It helps provide predictable turnaround times, and most importantly, you have full control over your orthotics and prosthetic designs and clinical outcomes. Now let's say that there was a small O&P clinic that was interested in using this technology, but lacked the building space to incorporate a carver. Instead of giving up on acquiring the entire solution, the facility can still consider the CAD portion around digital scanning and design. With only these tools, the clinic can still scan their patient and modify the shapes through a CAD program. Once they're done, instead of milling the mold in-house, the clinic has to outsource it from a third-party company. To do this, they can easily send those files via email to a central fabrication facility. These central fabrication companies, or CFABs, normally have carvers to manufacture molds for their clients. Once it is carved out, the mold is shipped back to the small clinic. Note that it's also possible for the CFAB to fabricate the definitive devices as well for their clients. Overall, this flexible model allows practices with smaller budgets and clinical spaces to reap the benefits of using CAD/CAM technology. Now, even though this offers a fairly low entry to using CAD/CAM technology, there are still some factors to consider. The first one being the recurring cost that comes with outsourcing services. Relying on a CFAB means that you have to consider the cost of producing the molds as well as the shipping fees involved. If you work on a small clinic, the volumes may be adequate enough to accept these costs. However, a practice that is consistently outsourcing high volumes of carvings or devices might see these fees to be much more substantial. Another thing worth noting is the loss of complete control over the outcome of your work. Central fabrication facilities are not always perfect and sometimes can send inaccurate molds back to their clients. On top of that, you might also have to rely on slower turnaround times by using this model. Finally, to even use a CFAB, you have to make sure that they can accept your CAD files to begin with. There are numerous different file formats for a 3D shape, and not all are accepted for certain types of carving machines. Before working with one, it's worth taking the time to discuss this with your local central fabricator to avoid any unnecessary compatibility issues. If you have a facility large enough to house a carving machine, you can start doing central fabrication work yourself. Providing CFAB services is a great opportunity to expand your business and develop a positive reputation with local clinics. Regardless of which business model you choose, this technology empowers O&P professionals with modern tools to work faster with accuracy and precision. While we discussed the different flexible approaches for using CAD/CAM in an orthotic or prosthetic facility, we still have not looked at the actual benefits of the technology itself. So what are the advantages people can expect to see with this sort of solution? Becoming more efficient and offering better patient care are two of the biggest advantages that O&P professionals value from CAD/CAM technology. Efficiency can come in a variety of ways. It can mean significant time savings associated with incorporating a digital process. It could also mean spending less money on resources such as plaster or even hiring new staff. For clinics that struggle with plaster cast storage, that no longer becomes an issue when everything is stored in a digital format instead. 3D scanning has made great strides in reducing plaster usage for patients. On top of that, scanning is fast, safe, and simple, so the patient can feel at ease. But it doesn't stop there. With digital records of patient devices, subtle design tweaking or replicating orthotics and prosthetics is extremely easy. Adopting a digital process to avoid plaster is a pretty amazing transition for people in our industry. While traditional O&P fabrication methods work for some people, the advantage of having a cleaner and less physically demanding workflow is hard to pass up. A quality 3D scanner will often trump plaster casting patients when it comes to producing better fitting devices. Even outside of the patient room, digitally modifying shapes at a detailed level gives orthotists and prosthetists more control over exactly how much correction they want to apply to their devices. Overall, there are just some things in CAD that can never be done on plaster. The beauty of working in a CAD system is that you have the ability to standardize and replicate your workflow with ease. If there was a device that you made that worked really well, chances are you might want to copy that workflow for future devices. For instance, with Vorum's CanFit design software, you can actually save repetitive modifications and apply them to the orthotic or prosthetic devices that require them. These types of shortcuts can become highly valuable in standardizing processes across all clinicians, and it can even be used to help train new ones too. Digital documentation is a real key piece when you think about the importance of financial reimbursements and justifying your care for your patients. The more information your CAD program can provide for you, the more effective it will be to build your case. Similar to the first point about becoming more efficient, having a digital solution can drastically reduce turnaround times for your patients. Those who use CAD/CAM often see the benefits of long-term savings. As mentioned earlier, an experienced CAD/CAM user can save money on things such as materials or hiring new staff. It can also reduce the labor hours on fabrication work and allocate that time towards seeing more patients. Finally, for some O&P facilities, owning a digital manufacturing process could mean offering more value for their patients. By differentiating themselves from other local businesses who might still be working with traditional methods, like I mentioned before, having a full CAD/CAM system also introduces the opportunity to offer additional services such as CFAB work for local clinics. The additional services and advantages introduced by this technology can easily help a business grow. I hope many of you found this introduction insightful, or at the very least, a good refresher on what digital technology can really do for the industry. With that, I'll be handing it over to Chris Sokolov, who will be going over an introductory overview of 3D printing on P devices.
Thanks, Nam. Hi, everyone. My name is Chris Sokolov, and I've worked at Form for the last 5 years as an implementation specialist. I'm going to continue our discussion today by providing an overview of the various print technologies that are currently being used for 3D printing O&P devices. So additive manufacturing comprises many different technologies, but the 3 primary groups of technologies that are used in O&P today are filament or pellet melting, referred to as fused deposition manufacture or fused filament fabrication interchangeably, resin curing systems that use technologies such as stereolithography and digital light processing, and lastly, powder technologies such as multi-jet fusion and selective laser sintering. At a very high level, the filament or pellet melting process involves melting a thermoplastic and pushing it through a nozzle. The plastic then cools and solidifies, ultimately leaving behind the desired shape or part on a print bed. Layers are typically built from the bottom to the top. These printers can generally be range from very advanced and costly to cheap and easy to use. A hobbyist printer that your friend has or the one at the local library is likely of this type. Resin systems are kind of similar to FDM processes in that the part is attached to a print bed and printed layer by layer. But the big difference with this one is that the print bed is upside down and the part is then pulled up out of a bath of resin with the part upside down. Instead of melting it with a thermoplastic, the resin is cured with light, often a ultraviolet source. And lastly, the powder-based systems work a little differently than both of those previous two. Instead of relying on a part to be secured to a print bed, the print volume is filled with a thin layer of powder, and the desired portion of this layer is then solidified, typically with maybe a laser. It depends on the specific powder technology in question. Once that layer is done, a new layer of powder is deposited and the process repeats. Starting with fused deposition manufacture or fused filament fabrication, this is the most common and accessible technology. Just going through some of the advantages and disadvantages of this technology. Right now, it tends to have the widest availability of materials. Really, the only requirement for materials is that they must be a thermoplastic, meaning that they can melt and be pushed through a hot nozzle. Another advantage here is that they tend to be the most practical for reforming after print. So because the parts are made by melting the plastic, once the print is finished, those parts can then be heated to below melting where they can soften and you can make small adjustments similar to how you would make a conventional thermoplastic device. Another advantage here is that printing multiple items at the same time will be faster than printing one after the other, as there's going to be some efficiencies with how the nozzle moves. Typically, if you print 2 identical items at the same time, if it was by itself, it may be 1 hour. If you're printing 2, it might be 1 hour 30, 1 hour 45. The disadvantage with this technology is that it tends to struggle with complex overhangs. So if you're printing a device that has a part that has no material underneath it, you will either need to look at compromising with respect to the orientation of the device in the printer in order to alleviate that, or else you may have to print support material, which will then need to be removed after you're done printing. Before we go into the best applications for filament, we're just going to start off by saying there's no hard and fast rule about which technology should be used for a specific application. We're just going to discuss a few options and tell you why we think one technology might make a better candidate than another. So for filament-based systems specifically, they are currently the fastest in terms of grams per hour of material deposition. Where this becomes relevant is for larger device types, such as sockets and TLSOs. Even with that considered, fastest FDM printers using the largest nozzle available is still going to take many hours, upwards of 6, to print a TLSO. So for most print applications, there's a size at which things start to make more financial sense. For FDM in particular, we tend to find a device is about half the size of another in all 3 dimensions. Talking about height, width, and depth, it's likely only going to have about 1/8 of the amount of material, and thus it's going to print about 8 times faster. So all things being equal, those 2 devices are going to take a similar amount of time to manufacture conventionally, but the smaller one is going to make more sense to print than the larger one in terms of time and cost. Coming back to our other technologies, for resin curing systems, we have stereolithography and digital light processing. Stereolithography involves a UV laser curing the polymer resin, and digital light processing also uses UV light, but involves a projector that is able to cure the resin in a layer at a time. So the advantage of this technology is that overhangs are easier to deal with than filament. You do need to still print supports, but because the parts are being printed upside down, these supports are in tension rather than compression. So they can be thinner and they're going to be easier to remove as a result when the print is done. Resin curing systems are also very good for fine detail. Usually this comes at the cost of time, but with an SLA printer, the smallest feature size is going to be determined effectively by how concentrated your laser is. And this excellence with respect to small feature size is likely why these printers are in wide use for things like tooth alignment with the Invisalign technology and custom hearing aids as well. Another advantage here, because the print time is effectively determined by the largest Z value of the part, or the number of slices, printing 2 or 4 items at a time instead of 1, assuming the overall height is the same, is going to add little to no time. The disadvantages here, right now there's fewer choices for materials, so in our experience we see that this tends to change pretty rapidly. Another disadvantage here is that there's extra post-processing steps involved. Things like cleaning off the remaining resin, and then not very often the part needs post-curing. You can automate that somewhat, but it will require another piece of equipment to do that UV curing post-print. Another thing that's involved is the materials consideration. So because this technology involves materials undergoing a chemical change when they cure, that's likely going to be more challenging to deal with from a biocompatibility standpoint when you're looking at ISO or FDA standards. And the last part about this is because it is a chemical reaction for curing rather than melting, you can't heat reform the part after you take it off the print bed. We're looking at the applications for this. As I previously noted, resin-based systems have found themselves a productive home in dental and hearing aid production. These parts generally require fine detail, and the small sizes of these devices complement one another very nicely. Further, neither part is going to undergo significant loading, so strength of the part is going to be less of a concern. In terms of this becoming widespreadly used in O&P, we're going to have to see biocompatibility test results for some of these materials so that we can make sure that they're all right for human tissue contact. For powder technologies such as MJF and SLS, the advantages of this technology tends to be that it's going to have the fewest issues over the other two with overhang of each part. Because effectively the print is going to be supported in a bin of powder as it prints. It's currently the best technology for fancy cutouts and lattice structure for kind of the similar reason. When it's printing, the part is effectively resting in its support material. But also these printers tend to be able to print small feature sizes. And also, again, it's not going to require any supports for some of these more intricate designs. And lastly, sort of similar to SLA, again, the print time is effectively going to be determined by the largest Z value of the part, or the number of slices. So printing, more items than one is effectively going to add little to no time. Some of the disadvantages here: there's a long cooling time required after print. Multi-jet fusion's been a really big improvement compared to SLS in that regard, but they still both require significant cooling time of the part before it can be used. Typical times are 1-to-1 between print and cooling time. So for a full print volume on a large multi-jet fusion, that can be 16 hours of print time, 16 hours of cooling time. Another disadvantage here is that for now, it's mainly nylon that's being printed, like a polyamide or PA. But very recently, HP has been adding more materials such as TPU. The last part that we're unclear about right now, it may be possible to reform parts once they come off the printer. HP currently does not recommend that, but it may change over time as experience is gained. So what are the best applications of powder technologies? The two applications we are going to look at, we did for very different purposes. So the first two that we think tend to go hand in hand: cosmetic covers and wrist braces. They're interesting applications in that there tends to be sort of intricate designs that are involved, and the powder technologies are really good at getting those fine details in there. For cosmetic covers specifically, when you're putting those on a device, there may need to be some areas where they're going to very intricately and precisely mate with existing hardware like pylons, foot attachments, or knee joints. So in those cases, it's really important to have that fine detail. The other application that we think is really well suited to this is in-shoe orthoses. And the main reason for that is because the parts have one dimension that's quite small relative to the others. So in the case of in-shoe orthoses, you have really long and wide parts, but the actual thickness is quite small. For powder technology, what that means is that it's easier to stack them inside the work volume, and that's going to improve your overall time per part. You can't really do that with devices like sockets and TLSOs unless they were able to nest inside each other. So with those, it's kind of harder to get a reasonable time per part. That about covers my part. I'm going to hand things over to Taryn now, who's going to discuss how to implement CAD/CAM and or 3D printing in your facility.
Thanks, Chris. I'm Taryn McCready, and I'm an implementation specialist at Vorum. I'll be talking about making the transition from conventional fabrication to digital fabrication. The first thing that we're going to do is review the elements of a CAD/CAM system and then go into what would be the steps to move from a conventional plaster-based production model into a digital system with carvings, and then take the next step in that journey towards implementing 3D printing into production. Of course, the system can be broken up and central fab used for parts of the process, but for the sake of discussion, we're going to assume all steps are currently done in-house using conventional techniques with a desire to go fully digital and possibly into 3D printing. The first step we'll replace is the casting step. Regardless of the casting medium that you use, be it plaster, fiberglass casting tape, alginate, or foam boxes, the image of the patient that we will capture is now going to be digital rather than physical. This may be a 3D scan, as pictured, or it could be a series of manual measurements and photos. So what differences should we expect when compared with conventional casting techniques? There are some good things. First, contactless scanning is much more repeatable, both between scans performed by one practitioner or different scans of the same patient by different practitioners. This has long been a benefit of scanning in that it removes an element of uncertainty around questions like how tight was I pulling the casting tape. Scans are digital, and this means that storing them takes just some computer memory instead of physical space. This allows us to maintain records not possible with conventional manufacturing. Being digital, scans can also be transported for free and instantaneously. If you wish to consult a colleague in another city, state, or country, they're just an email away. Scans are virtual versions of the patient, and no material or time is required to fill the cast to create a positive. And while this isn't often considered, casts of a patient may be bringing back germs into your office, and now more than ever, that is a consideration that's very important in certain settings. So what's different? It's generally less practical to manipulate the patient during a scan the way that you might be accustomed to during casting. This, of course, is a change that you may learn to work with, and if so, it can be a benefit, because all of those manipulations will now be captured in the next step during the design, which can be good from a record-keeping perspective. If you can't get over the need to manipulate the patient during casting, there are still benefits to be had by casting the patient and then scanning the cast. Once we have a scan, however we arrive there, we'll then progress to the design phase. The design phase will effectively replace the following pieces of conventional workflow: the cutting and bending or twisting of the cast, filling the cast, stripping the cast, smoothing the positive model, and plaster buildups and pressure zones. The output from the scanner is a virtual positive model. Remember, there's no need to fill a scan. The scan can be manipulated in the design software to perform any twisting, bending, or translation-type motions that would previously have been done to the cast before pouring it. The advantages here are several. The amount of bend or twist is recorded in the software. Bends and twists can be more naturally applied and blended over a larger area, and instead of the narrow zones that are used for cut and correct operations on a cast. And bends in particular can be isolated into a single plane, AP versus ML, if desired. Since there's no filling of the cast, clearly there will be a savings of time in not having to strip the cast either. Smoothing can be performed in both the scanning application and the design application. However, using sensible defaults provided with the system, smoothing is often not required. It's simply built into the process. As for the build-up and pressure areas, CANFIT users have long enjoyed the automatic documentation of the design process, as the modification history is built into the action stack. There are a whole host of interactive tools that allow you to see the results of your changes in real time. And more importantly, there are saved modifications in the forms of regions and trim lines, and the macro ability of most tools to make modifying quicker and more consistent while preventing steps from being missed. Plus, if you have complicated cases or a particular doctor or surgeon that you work with, reports can be generated showing the changes done prior to manufacturing a device. Once all of those steps are completed, a finished design file is created to be milled. Looking back to conventional manufacture, the steps that we're going to replace or change are pulling the plastic or doing layups and trimming and polishing. In this case, we do have an extra step. In fact, it's not so much extra as it shifts from the design phase to the fabrication phase. As noted previously, there's no need to create a positive in order to do modifications. It is still, however, necessary to create a positive of the device to be manufactured if it's going to be done by thermoforming a plastic over a mold. So what do we have to do in this phase when using a digital carving solution? So first, we need to load the shape into a block in the VisualCam software. VisualCam is a tool, and it generates a toolpath file. This way, the machine knows how to make the positive model. It's very simple to use, and typically, processing time is less than a minute. And what you can do is place multiple shapes within the same carving job if the shapes are small enough compared to block size. Plus, you can also reuse blocks to cut down costs on materials. Once a toolpath file is generated, it's loaded into the carving machine, and the appropriate block is loaded and milled. The next step is very similar, though with some small differences that you should be aware of. First, carved foam blanks are much lighter than plaster positive models. So for things like TLSOs, this means that a single person, regardless of their stature, can easily move around any mold without worrying about OSHA considerations for heavy lifting. The other significant difference is a thermal one. When thermoforming on plaster, the plaster acts as a heat sink and causes uneven cooling of the plastic. The inside cools faster. Depending on where you live and work, you may even have to heat up your molds prior to pulling plastic to reduce this effect. When thermoforming on foam, the foam acts as an insulator and causes uneven cooling of the plastic, but this time with the outside cooling faster. This is no more of a problem than with plaster. It's simply different, and many companies have found different solutions to overcome this. Trimming and polishing is largely the same, but with a couple of exceptions. First, when trimming, because the foam is much softer, some users have found that trimming can be accomplished much faster with a jigsaw with a short blade. When extracting the mold from a closed shape, such as a socket, if there are undercuts in the foam, it may need to be destroyed a little bit differently, since using a chisel doesn't work the same way as it would on a plaster positive. So next, we're going to talk about adding in the additive manufacturing component to the digital workflow. There are a few important differences. First, we actually need to return to the design phase. So in the carving world, we only design the inside of the device. For additive, we need to design the entire device. And why? So when using conventional manufacture, the choice of sheet plastic, both type and thickness, will govern much of the final device's mechanical properties. When using additive manufacturing, we have to choose the material type that will govern part of the mechanical properties. But now we design in the thicknesses actually, in the design phase. And I say thicknesses because here we have an advantage in that thickness may not necessarily be the same everywhere. This can allow for a less bulky device while still being strong or stronger than a conventionally made device. The other thing that we'll want to do when designing for additive versus carving is define the trim lines in the design tool. There may be some times where you want to add holes after a fitting, in which case, no problem, you can certainly drill into the print after the fact. But for large windows on a TLSO or an AFO, when you only really want the device to exist over about half of the mold, you will want to define these zones to reduce material used and print time. And in the case of an AFO, if you were to print the entire model, you would almost certainly require supports as well, unless you were using a powder technology. Once we complete our design with thicknesses and trim lines defined, the output file goes to a different preparation software. I'll generically refer to it here as a slicer. The slicer performs a similar task, as does VisualCam. It takes the shape file and converts it to instructions that the machine can follow to make the part. While currently a bit more complex than VisualCam, we continue to make great strides in having easy-to-use print processes that require little interaction to reliably create a functional printed device. The finishing required in conventional and carving processes is far less because the final print will already be trimmed out. The usual buffing of edges will still likely be required, but the finished device right off the machine is very close to what you would put on the patient. So next I'm going to hand off to Paul to discuss 3D print tools in CanFit.
Thanks, Taryn. Hi, everyone. My name is Paul Leray, and I'm one of the software developers here at Vorum. And today I'm going to be talking a bit about some of the 3D print tools in CanFit. So we're continuing to expand a lot of the 3D print capabilities in CanFit. Some of the things we support are uniform, variable, and constrained thickness controls, rounded trim line edges so that you get nicer 3D prints at the edges. Also, we have some steep surface detection, so you can tell if there are overhangs or anything like that that might not print very well or will need supports. We also have support for components. So these are things like socket adapters, strut adapters, Tamarack joints, and holes, as well as embossments. So these can be images or text that get placed onto the surface. So I'm going to bring up CanFit and I'll do a little software demo of some of these features. Okay, here we have TT shape, and the first thing I'm going to do is I'm going to go to the 3D print tab and set a uniform thickness across the whole shape. So I'm going to set this to 3 millimeters. And you can see here there's the 3D print outer shell that is now visible in your 3D view. as well as in the 2D view. So I'm also just going to show you that you can adjust based on a constraint. So I'm setting a plane here, and what we want to do occasionally is strengthen the bottom of the shape. The reason why we might want to do this is to have extra support for something like a socket adapter, which is what I'll move on to after showing you some of these parts. So you can see here that that it's a bit thicker at the bottom now. I've just increased it to 5 millimeters just to give a little extra strength at that bottom part of the shape. The next thing that I want to show you is the steepness. So I'm going to turn off this 3D shell here, and we're going to enable the diff map. You can see we have a steepness option here where you can see which parts of the shape overhang. So anything that's overhanging too far, if we look off the side here, there's some areas where that's going to stick out. Now, when you're 3D printing, this is something you have to consider in terms of what kind of supports you might want to add. But there are some areas where you might be able to just touch it up inside Canvit so that you won't actually need supports and you will get a better 3D print. So at the bottom, you can see, obviously, there are some very horizontal areas in there. Those I'm not worried about because we are going to put a socket adapter at the bottom. But this area, it's maybe a little too, or it sticks out a little too far. So what I'm going to do is go into our sand tool, and I'm actually just going to smooth this out a little bit. So I'm going to click OK, and you can see there's still a little bit of an overhang there, but it's not as bad as it was and should give a pretty decent 3D print. So you can adjust this based on your settings. Particular 3D printers might have, and materials might have different requirements in terms of what they can handle for those kinds of angles in terms of sticking out of the shape. So this is completely customizable, and you can set that according to your use case. So let me just turn off the diff map now, and I will go to the Components tab. And we're going to add a socket adapter. So if I click here, we can see we now have a representation of that adapter on the shape. And one thing we want to keep in mind is that these adapters should be roughly in the middle of your shape. So we have this center of gravity marker, which you can see over on this left-hand side. So what I'm actually going to do here is adjust the shape a bit and just move it over just a little bit, just to get it kind of closer to that center of gravity. We don't want it sticking out past any of the sides, but we do want to verify that the socket adapter is going to be roughly in the middle of the shape. So that looks okay. And what I'm going to do here is hit preview. And you can see we have a socket adapter on there. So things look pretty good here. If there are some other issues, you could adjust some of these values to get it kind of the way you want it. And once you're satisfied with it, click OK. And this is now on the shape. So you'll see it continues to exist as a separate entity. So you can continue to make modifications to your surface without it being affected by the socket adapter. So this is something that gets applied as you create the final 3D print outer shell. All right, the next thing I want to talk about here is Tamarack Joints. You can see I have an AFO open here, and there are two separate sections of the shape denoted by these trim lines. So I'm going to navigate to the Components tab, click Add Component, and I'm going to choose a small Tamarack joint. So you can see in the comments, uses the lateral and medial malleolus landmarks. So these will get put directly on those landmarks. And if you need to, you can also place them manually, but it's nice that it will pick up on those landmarks and put them there. I'm going to click OK. So we've got one on there now. Just going to click Add Component again. And you can see after I've clicked this other one that we now have two on there. I'm going to click Preview. And as you can see, there's been some cutouts made to accommodate these Tamarack joints. And they have adjusted the surface to make room for them. I'm going to click OK. Now, I just want to show you that typically you would go to this Output tab, click 3D Print. This is where you'll go when you're ready to export your shape. You can pick your density, and you can see as you rotate around the shape here, this has the Tamarack joints embedded into that final surface. So from here, you can export to STL and then go to the next part of your 3D print pipeline. All right, I'll move on. So here we have another AFO shape. Again, you can see by the trim lines that this is in two parts. Now, what we're doing for this one is we're actually going to add a strut adapter. So this is something where we will want to add two parts. And you can see that, you know, this looks like it might need a little bit of rotation. So we're going to adjust that a bit to place that on the shape. Click OK. You'll see that I didn't have to place it. It just showed up on that back of the heel landmark. And now as I go to add another one, it's going to add it to this calf landmark. Again, just going to adjust the rotation a bit. And click OK. You can see we've got these adapters placed on the shape. Now, if I go hit preview here, you can see that these are now on the shape, and it has room for mounts. So after you 3D print that, you can mount a strut to these adapters. So the other nice thing I'll point out too is we do have nice rounded surfaces around all the edges of these trim lines. So that does two things. One thing, it makes your 3D print results come out more nicely. But it's also a comfort thing as well. It makes it, you know, a little more comfortable to put on. So, you know, we don't really want to have sharp edges here. So, all right. And I will move on. So that's all I want to say for components at the moment. I will mention that we also support holes. So if you have some additional custom hardware that needs to get mounted on, you can print the holes directly into the shape. Now I want to talk about embossments. I'm going to open up this TF shape. So embossments, they can be created using either custom images or text and get applied to the surface of the shape. They're similar to components, and they're actually accessible through the components tab. So if if you want to add, say, your company logo onto the shape, what you can do, just going to give this a name, and going to load an image here. CanFit embossments. Here we go. So here's our Vorum logo. I'm going to place it on the shape and adjust the size. So something like 50 millimeters. And click preview. So now you can see that logo is on the shape in 3D and will show up in your 3D print. So we're going to click OK. That's on there now. Again, like components, you can continue to modify the surface of the shape, and the embossment will get applied and follow that surface when the final 3D print output is generated. I'm going to now add some text. So let's add that here. Just give it a name, sample text. And these can be things like, patient IDs, company names. Here I'm going to put a serial number, 1, 2, 3, 4, 5. And let's actually make this vertical. So this is similar to images. Just want to make sure it's in the right spot there. Now there are different resolutions for text. Sometimes, you want to have very, very crisp text. And if so, you can choose a very high resolution for your text, which will get applied to the 3D surface. Of course, this creates a lot more points, a lot more data to work with. So usually it's not needed to go quite that extreme, but it is available if needed. So the other thing I'm actually going to do here, of course, we can raise the text, which is embossing, but we can also actually deboss, which is to cut the text into the surface of the shape. So I'm going to hit preview here. And as you can see, the text has been applied to this surface. And not only that, it is actually cut into the shape instead of sticking out. Now, the reason you might want to do this is in cases where you're concerned about maybe pieces will rub. Having it cut into the shape like this, you don't have to worry about it catching on things. And it also is a feature that you can use if you're placing an embossment on the inside surface of the shape, which is also possible. So that's something where you definitely wouldn't want anything sticking out but it is possible to have something embedded into the surface. All right, that's it for me. With that, I'm going to hand it over to Chris Hanford.
Hi, I'm Chris Hanford, Product Manager here at Vorum. I'll be walking you through some of the common challenges and hurdles to be overcome if you yourself are looking at getting into 3D printing in O&P. Anyone who has ventured into 3D printing in this industry has seen firsthand that there are many challenges to becoming successful. I'll highlight some of the key ones here, but it's important to note that at the end of the day, none of these challenges are inherently showstoppers, meaning there are ways to overcome these challenges and have success in 3D printing for O&P. The first challenge I'll mention is that there is simply a lot to learn when getting into this technology. So why is that? 3D printing for O&P has been around for decades, but it's relatively recently that technology has advanced to a point that it makes sense to be used in O&P. When looking at 3D printing applications in industry, we see it's often used for prototyping and making one of something. This aligns very well in O&P, as what we provide are usually one-offs. A check socket itself is a prototype for the final fit and function of the definitive socket. What sets O&P apart from industrial prototyping is the fact that the model is not just a visual and tactile representation of a final product. In O&P, that one-off can also be the definitive, which must stand up to the patient's weight under load while standing, walking, and doing other activities. As the challenges in O&P are unique, it's really been the O&P community that has taken the lead on developing 3D printing to be something effective and practical for our industry. With that, there has been lots to learn. The main 3D printing technologies, that is powder-based like SLS or MJF, thermoplastic like FDM, and resin-based like SLA, each have their own advantages and disadvantages, different materials, and also various shape design and slicer software tools. With so many potential solutions out there and not a ton of experience yet, many O&P clinics and central fabricators have taken it upon themselves to learn the technology and attempt to dial in a process that works. But this takes time and takes real patient fittings. One key thing to learn is finding a design that not only replicates traditional techniques, but also leverages the printer's capabilities to offer better outcomes for the patient. As well, the fact that the technology seems to advance each year or less, it can be a challenge to keep up with the latest information and best practices as the technology evolves. Another challenge, along with learning curve, is around learning how to ensure you're meeting regulatory requirements. For example, with the FDA, they have issued guidelines around 3D printed custom devices. While these are not difficult to work around, they do require you to do your homework and can impact how you go about producing devices with the technology, all in the interest of improving safety for the patient. In the FDA case, there are exceptions to some requirements when the device is custom, though you have to carefully control your process. The FDA states that depending on the type of technology, it can be necessary to control the placement and orientation of your shape within the printer so it is consistent with how it has been done and tested successfully in the past. For example, with FDM printers, as layers are printed horizontally, the device will be stronger in the horizontal plane, but weaker in the vertical direction. Because of this, you have to tailor your shape alignment in the print volume in such a way as to optimize strength where it's needed most when under load. And once you understand the orientation that works best, you must keep it that way for similar devices in future. There are also shape placement factors when working in powder-based materials, like in SLS or MJF technology. With these technologies, orientation of the device has less of an impact on device strength, but on the flip side, as the volume cools from the outside in, you may get different strength characteristics for devices printed near the outside of the volume than you do near the center. Another guideline from the FDA refers to the storage of the print materials. Usually this refers to keeping the material in a dry, warm environment to reduce moisture before it can be used in printing. If the material contains moisture, it can cause discoloration in the material, and worse than that, it can introduce points of weakness in the device that can cause breaks under load. Another side of the FDA guidelines are related to biocompatibility. It's important to know that the material you'll be using in the device will not cause any issues for the patient, such as abrasions or allergic reactions to the skin. It would be very expensive to go through full biocompatibility tests on your own, but fortunately, it's possible to exempt yourself from these tests if you know that the material and print characteristics have passed biocompatibility tests before. It's important to note that even if a material in sheet form has passed biocompatibility tests for a thermoformed style device, that does not necessarily mean it is biocompatible when 3D printed from a spool, as the characteristics from the material may be different, simply based on how it's processed in the making of the device. Aside from the material issues mentioned previously, there are other challenges around materials in 3D printing, and they do differ based on the type of technology used. Materials are so dependent on the type of technology that it's hard to discuss one without the other. In resin-based printers, like SLA or DLP, once you print your device, you have a secondary process to cure the resin. You have to be a bit careful on the biocompatibility, as any uncured resin can be hazardous to the skin. SLA has one challenge relative to the other technologies due to the fact that it's not practical to create any sort of infill pattern, as it would result in uncured resin within the device walls. With SLA, you have fewer material options to work with. We have not seen yet many clinical applications using this technology. With FDM, there is a wider choice of materials, and compared to other technologies, it can offer the quickest turnaround for a printed device. Some FDM materials can be reheated in localized areas to make adjustments for fitting. However, the FDM-based materials, you do need to be more careful with shape overhangs. And in many cases, you'll need to design in some supports or scaffolding to support the shape as it's being printed. You also have to be careful that you're getting sufficient interlayer adhesion. Otherwise, you'll increase the likelihood of failed prints or weak points in your final device. With SLS or MJF, it does allow for fancy lattice structures. There are opportunities to stack more devices in a single print volume, but there are drawbacks to this technology as well. There are fewer material options as well. You have to be patient. Printing a job can take the better part of a day to complete, and once that's done, you need to wait an equal amount of time to cool the material, meaning in many cases, you'll need about 2 business days before you have a part ready for finishing. The technology is still quite costly, so in our experience, it makes sense for a central fabricator doing a high volume of prosthetic sockets or cranial remolding helmets, but isn't feasible for most individual clinics. One of the biggest challenges with any of the technology is around doing things consistently. All technologies, and especially FDM, is reliant on maintaining a consistent process. Any moisture in the material or in the environment, or deviations in filament thickness can lead to failed prints, such as the image shown here. If the bed isn't heated at the correct temperature, you can also cause problems with the device adhering to the bed and also leading to failed prints. With MJF, this is not specifically an issue, but you do need to be careful about how you align the devices within the print volume. If you pack shapes any closer together than 5 millimeters, you can have issues in those areas. "3D printing is still generally slower than traditional techniques, but while turnaround time may be increased, technician time should be decreased, so there may be an overall cost savings. With lengthy print times, capacity and throughput become an issue. What that means in practice is that as your workload grows beyond the output capacity of the printer, you must invest in additional printers. Printer speed is something that is continually advancing. In FDM, we're already seeing print times in the order of 2 to 3 hours for a pediatric AFO or adult check socket. This is quite a bit faster than was possible just a couple years ago. There are also device size limitations with most of the printers on the market. While print size limits can prevent you from printing a large device like an adult spinal brace in most machines, the flip side is that with the larger sizes, the time to print exceeds the traditional methods by an even greater extent. So the economics are likely not there to print these very large devices. Cost is an obvious factor in getting into 3D printing. But just like with CAD/CAM, there are ways to get into the technology in small steps. There is such a wide variety and range of technologies available, and with FDM especially, prices for a machine can vary drastically, from the hobbyist end of the spectrum to the industrial grade printer end. If you only want to learn about 3D printing and start taking baby steps toward production, a low-end hobbyist machine and some freeware CAD tools can certainly provide that. A couple $1,000s will get you up and running. If the purpose of the investment in the technology is to use it for clinical fabrication, then you'll be looking at an industrial grade solution. With the larger investment, you need to understand all the related costs to understand the impact to your bottom line. Aside from the price of the machine, you'll also have costs for material on a per device basis. What's often not considered is the impact on costs related to failed prints. If a print fails, you not only have the added cost of the new material, you also have the cost of lost time and potentially overtime for the technician who has to stay late to load the new job. You need to consider the reliability and consistency of the printer output to determine the true cost of an investment in a 3D printer. The more reliable the machine you are investing in, and the better control you have on the whole process, the less significant this becomes. With MJF, the economics of the solution can work well if you're able to fill a reasonable number of devices into the print volume each day. Conversely, if you only have 1 or 2 jobs per day to be printed, it likely makes more sense to leverage a central fabricator with the technology until your volumes increase. If you've already invested in CAD/CAM technology, you may be able to use your scanner and software to feed into your 3D printer. This can certainly reduce the investment in 3D printing. As well, the skills and processes you've put in place for CAD/CAM can be easily transitioned to additive manufacturing process. This can also help with the overall cost. To manage the cost aspect further, another strategy to see a return on investment faster is to identify and focus on devices that offer the biggest reimbursement for the smallest size. Prosthetic sockets and foot orthotics are devices that often make sense, and in the markets outside the US, cranial remolding helmets have also been successful in this area. Thanks for your time today. I'll now pass you over to my colleague, Jeffrey Chang.
Hello, I'm Jeffrey Chang. I've been working at Vorum for 20 years now, and I've cycled through most areas of the company, with the last 5 years or so in the research and development department, focusing on our equipment and most recently our foray into 3D printing. Even in just the last 5 years, there have been myriad developments in printing and design for printing. The way we're going to wrap up this presentation is to share some of our most important learnings and hopefully some nuggets that are useful to you, regardless of where you are in your 3D printing journey. Don't get too hung up on how I've split up the things we've learned. You may be brand new and know something I'm calling advanced, or you may be advanced but have not come across an issue I'm referring to as basic. Note also that most of what I'm going to talk about is what we have discovered on our journey, which may be different from yours, depending on the print technology or technologies that you're using, as well as the types of products that you wish to make. So, what have we learned? The basics. Again, don't get too hung up on the categories here, but this is really kind of some of the stuff that we've learned that I hope will be valuable for a lot of people who are just starting out. First off, just because you can doesn't mean you should. One of the first things I encountered when I got into 3D printing was everyone sending me to links to miscellaneous things on Thingiverse or other online repositories of 3D objects they wanted me to print. A couple of things became clear. Many items were not really thought through from the design perspective, considering additive manufacturing. Little figurines can be printed, but loads of supports are often required for FDM to get certain details right. Many items are much more efficiently made through conventional, say machining, for example, manufacturing techniques. A plate of constant thickness with a few drill holes in precise locations will frequently be better, stronger, and quicker to make with a milling machine. Along these lines, we must ask, regardless of the industry, why do you want to 3D print the thing? Certainly, starting by printing exactly what you manufacture today is a reasonable place to start, to get the hang of things. The end goal should be to make something that takes advantage of the technology. Do not change for the sake of change. 3D printing affords us many positives if we embrace them, including nearly fully finished devices, which means no variation between technicians for trimming, for example, more possibilities to uniquely control device properties in localized areas by changing thickness for FDM or internal structure for powder technologies, physically separating design and fabrication. Maybe you want to see patients and do design in city centers, but run larger fabrication facilities outside the cities for cost reasons. Next off, remember what you're trying to accomplish. This may seem silly, but we can't lose sight of our objectives. The objective shouldn't be to buy and use 3D printers. It's not your job to subsidize that market segment. Are you trying to serve your patients better by making better devices or somehow offering better overall treatment? Don't just make the same device with the new tech. Are you trying to serve more patients, possibly due to a shortage of service providers in your area? Are you trying to be more profitable? Because let's be honest, profit can drive a lot of decisions. Again, getting started you might not meet all or even most of the goals right away, but you should be working towards one or more of them. And lastly, and this is true across so many industries and so many applications, you get what you pay for. I'm not saying that there aren't some good deals out there. I'm not saying that if you want to start with a lower end printer that you can't even, or that it might not make sense for you. What I will say though, is there are generally some reasons for the price differences. We've tried some different printers at the lower end, and we've had more issues with the following. Inadequate heaters for both the bed and the nozzle. On the bottom end, printers may not have a heated bed. This will impact what materials you can print. Some materials, notably ABS and nylon, really want a heated bed. Otherwise, warpage in the first layers can frequently lead to the part coming unstuck from the bed. Even on mid-range hobbyist printers, the heater for the nozzle may not go high enough to support some materials like nylon or PETG. But even if they do, the throughput may be limiting in terms of the grams per hour rate of material deposition. What this means is that although you can make the thing you want, it may take 10 plus hours. The other major factor is installation, assembly, and serviceability. This part really comes down to what you want your 3D experience to be. For some who are more technically minded and like playing around with technology, the idea of assembling a printer from scratch and figuring out the missing instruction about the wiring might be appealing and feel like a victory. Maybe more of you, I suspect, are looking at 3D printing to make you better at what you do. In such cases, it'll be better to invest not just in a machine, but a process and a partner that will support you in what you're trying to accomplish. This just isn't going to happen with a generic industry printer for $500 or even $2,500. All right, moving on. What we've learned intermediate. For those of you who have done some printing already, depending on the materials you've used, you may have encountered this issue, which was so obvious when we started printing with PLA, which is much less sensitive to the issue. Some materials, nylon, for example, are quite hygroscopic. For those of you who don't remember terminology from your high school physics or chemistry classes, that means that the material tends to absorb water. The implication for FDM type 3D printing is that the water inside the plastic will become steam as the plastic passes through the hot nozzle during printing. That steam will produce poor surface finish and a weaker part. As such, it's important that materials be dried and stored appropriately to ensure the best quality prints. This is true regarding storage, pretty much regardless of print technology. For powder-based technologies, the concerns are similar. And for resin-based technologies, you need to ensure that the resins are shielded from light that could cure it permanently. Just because you can doesn't mean you should in V2. Integrated componentry. So you might recognize that title from the previous section, but here's another item. One of the advantages of 3D printing is the ability to integrate component pieces together. In other industries, this is often done because conventional manufacture is such that it's easier, cheaper, whatever, to make a part as an assembly of parts. 3D printing, we often hear, gives complexity for free. While not quite as simple as that, there is a lot to be gained. For example, the wrench shown here can be printed as a single assembly. This would save on making separate pieces, keeping track of them, assembling. There are real gains to be had if done right. That said, we don't want to get carried away either. For example, I could do a multi-material print with built-in flexible joints. This would save on assembly and possibly hardware, screws, etc. However, if my printed joint started to wear or fail outright, that might mean needing a new device completely. Where if I had designed and used a tried and tested joint like a Tamarack, then that piece would be replaceable on its own. The key piece here is thinking things through and not getting carried away. What we've learned advanced. Material consistency is critical. This one's a little like you get what you pay for in the section on basics. Stated simply, all filament is not created equal, even if the chemical composition is the same, and it won't always be. More on that later. There are other considerations that can have an impact on performance of your printed products. Because of the way that the filament is pushed through the nozzle by the extruder, if the filament diameter varies a lot, then you can have areas of your print with too much or too little material. Too much will mean blobs and oozing and bad surface. Too little may cause voids and weaker areas. Not only do we care about the size, but also the shape. If the filament is oval, then depending on which way it is facing relative to the extruder gear, it may push too much or too little, even if the cross-sectional area is appropriate for the size. As to chemical composition, different coloring agents can have an impact on strength. Studies found that typically natural and black are strongest. Beyond that, for filaments that are a blend of different plastics, PHA, PLA, for example, the ratios may be different from one vendor to another. For different types of the same plastic in a blend, for example, nylon 6 and nylon 12, again, there may be variations in the ratios. Lastly, with additives, such as carbon fiber, there may be different amounts as well as different fiber lengths, all of which can impact strength for a given application. This should look familiar. Just because you can doesn't mean you should. Version 3. Another area that has seen some growth is the use of complex lattice inside of a print. The lattice may be used to impart different mechanical properties. For example, being more flexible than if it were solid in a given area. It may also be done to reduce weight in a zone of a part that is not significantly stressed. Where we do need to be careful in O&P, however, is having open lattices. While they can add flexibility and breathability, they also represent a very hard to clean area. For something like a cosmetic cover where the product in question has little to no patient contact, it may be less of an issue. But for something in direct patient contact, you'll want to have a surface that can be easily cleaned. And depending on the material properties, really thin bits like lattice are going to be more easily heated to the point of warping if, for instance, you were to try cleaning it by putting it in a dishwasher. And with that overview of learnings and insights from our 3D printing journey so far, that about wraps it up. Thank you for taking the time to listen to our workshop today. I hope it was insightful, full of learnings, and perhaps even inspired you to look at ways to optimize your facility's workflow. Whether you've had a traditional plaster workflow and want to modernize your practice by going digital, or you're already using CAD/CAM in your facility but haven't been able to find the kind of success you'd like to see, reach out to us. We'll find a way to support you with our over 30 years of expertise in helping O&P practices grow their businesses and help more patients. It's understandable with the amount of technologies that are out there today, it can be overwhelming when deciding on what solution to invest in. However, no matter your clinic size, your success will depend on what partner you choose for your CAD/CAM adoption. As Nam mentioned at the beginning of this workshop, Vorum was the first company to introduce a digital solution for O&P and has been leading the industry ever since. We're now on our 32nd year and proven in well over 800 installations across the world. From small single practitioner clinics to large multi-location institutions like Shriners Hospitals for Children, we've seen many customer success stories of Vorum users seeing productivity gains of 400 to 600% from adopting a digital workflow. That's because Vorum is the only end-to-end solution provider that provides non-contact scanners, 3D design software, and automated mold carvers, all with a single point of service. If you're looking to take your business to the next level by producing better fitting devices and providing a better patient experience, you can reach us via phone at 604-321-7277 or send us an email at info@vorum.com. We'd love to hear any other comments, questions, or feedback too. Feel free to send it in the chat box and we'll be happy to respond. Lastly, stay connected with us. Follow our social media channels on Instagram, Facebook, LinkedIn, and so on to keep up to date with our newest content. We post regularly on all the platforms, so if you found value in this workshop, you'll be sure to like the content on our socials as well. Thanks again. Bye for now.